Jai Hind everyone, I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, I'm going to take a lecture on the topic graphite and fullerenes. Now, these graphite and fullerenes, they are nothing but the allotropic forms of carbon. Carbon exists in two different allotropic forms. They are crystalline and amorphous. And the crystalline form includes diamond, graphite and fullerene, whereas the amorphous form, it includes coal, charcoal and lamp black. So today, the first that I'm going to discuss is the graphite. Now, graphite, coming to the structure, graphite is a two-dimensional flat sheet-like structure, and each atom is a hexagonal net of carbon atoms. Here the carbon, they are joined in a form of a hexagon, and they may be regarded as few systems of benzene rings. Now these different layers of graphite, they are held together by weak van der Waals forces, and the carbon-carbon distance between the carbon-carbon is 1.41 angstrom, and the distance between the two layers of graphite sheets is around the order of 3.35 angstrom. Alright, and the interlayer distance is large than the twice of the covalent radius of carbon in graphite. In case of graphite, only 3 of the valence electrons of each carbon atom, they are involved in the formation of sigma bond. Here, therefore, graphite is sp2 hybridized, and the 4th valency of each carbon is free. Coming to the electronic configuration, here you can see carbon C6, 1s2, 2s2, 2p1, 2s2, 2p2, where 2px1 and 2py1. Here only 3 of the valence electrons, they are forming the bond, whereas one valence electron is free to move. Therefore, carbon atoms in graphite are sp2 hybridized. This is the structure I am showing. The sp2 carbon has 3 hybrid orbitals at an angle of 120 degrees in one plane, and a hybridized orbital at right angles to the plane. So this is the hybridized orbital which is at right angle to the plane of the molecule. Now each of these sp2 hybridized carbon, they combine with each other to form a sheet of hexagonal arranged network. So each carbon atom contains an unhybridized p orbital. Together, due to resonance, they form rings of delocalized electrons, whose one part lies below the hexagonal plane and the other part lies above the hexagonal plane. Now coming to the types of graphite. Graphite exists in 2 different forms. One is the alpha graphite and the other one is the beta graphite. Now in the case of alpha graphite, here the layers, they are arranged in the sequence of AB. That means the 3rd layer is going to be exactly identical to the first layer. Whereas in the beta graphite, the layers, they are arranged in the form of ABC. Now, both the graphites, they can be interchanged into one another. Heating, it converts beta graphite into alpha, whereas the grinding process converts the alpha graphite into the beta graphite. The bonding between the layers is so weak that graphite cleaves easily between the layers, which accounts for a remarkable softness of the graphite and used as a lubricant. Now these sheets, they are around 3.4 angstrom apart, and these sheets, they slide over one another. Therefore, graphite can act as a good lubricant, and it is a good lubricant because friction between the layers is very less. The wide spacing of sheet also means that the atom do not back together to fill the space very effectively. Therefore, the density of graphite is lower than that of the diamond. So, since there are distance between the sheets, therefore, the graphite is lower in density in comparison to the diamond. Since carbon forms strong covalent bonds, therefore, the melting point of graphite is high. It is insoluble in water and organic solvents. Now, these pi electrons, they get delocalized over the whole sheet, and due to these mobile electrons, graphite conducts electricity, but not from one sheet to the another, but only within a sheet. Now, graphite is thermodynamically more stable than diamond. Its free energy of formation is 1.9 kilojoules per mole. So, thermodynamically, it is favorable for diamond to convert into graphite, but they do not do so. Why? Because of the high energy is required for the process. The reverse process is not thermodynamically possible because it requires very high energy conditions, and graphite can be converted into synthetic diamonds at 1600 degrees centigrade and the pressure of the order of 50,000 to 69,000 atmosphere. When an electric spark is struck between the two graphite electrodes, soot is produced, which is mainly carbon black, and it contains significant amount of carbon-60 clusters, and it is also known as Buckminster Fullerene. So this is the structure of graphite. Here you can see that there are 6 atoms joined together in the form of hexagons, and the pattern of the sheets you can see, this is the A, this is the B, and C sheet is exactly the form of A sheet. That means they are AB type, or it is the alpha graphite. So there are covalent bonds between the carbon, and the distance between two carbon atom is of the order of 1.42 angstrom, and the distance between the two layers of graphite is 3.4 angstrom. And these are the weak van der Waals forces which are existing between the different layers of graphite. Now, the delocalized electrons in the unhybridized p orbital are free to move anywhere within the sheet. Each electron is no longer fixed to a particular carbon atom. Because of these free electrons, graphite is a good conductor of electricity. There is, however, no direct contact between the delocalized electrons in one sheet and those in the neighboring sheets. Now, coming to the next allotropic of carbon, which is fullerene. Now this fullerene was discovered in the year 1985 by Smalley and Croto in Rice University, and they got the Nobel Prize also. Now, it was discovered during the experiment of laser vaporization of graphite rod under high vacuum chamber. Now, this is because the graphite sheets, they break down to form spherical fullerenes. This allotrope is properly known as Buckminster Fullerene in the honor of the architect Buckminster Fuller, who designed dome structure based on hexagons and pentagons, which resembles with the C60. Now, coming to the structure of fullerenes. These fullerenes, they form a cage-like structure, having the formula either C60, C70, C80. Now, all the carbon atoms in C60 are on the surface. Hence, they are called buckyballs. The structure of C60, it also resembles to that of the soccer ball, and it consists of 20 hexagons and 12 pentagons, with a carbon atom which is present at the each vertex of the polygon and a bond along each polygon edge. Now, the only restriction in the structure is that the two pentagons, they cannot touch each other. They should not share. The two pentagons, they should not share a single side. Coming to the diamond, here you can see the structure of fullerene. This is a pentagonal ring. Here you can see the pentagonal ring. There are the hexagons. All the structures are the hexagons here. This is also the hexagon. Here you can see that a single pentagon, it is surrounded by hexagons. That means two pentagons are not going to meet each other or share a common side. Now, the diameter of fullerene is around 0.7 nanometers, and it contains around 30 double bonds, and it has a face-centered cubic structure. It acts as a semiconductor, and pentagon sites in C60, they are more strained than hexagonal sites. Therefore, at high temperature, molecules, tends to break down at pentagonal site. Obviously, as the number of sites increases, the stability of the ring structure also increases. Coming to the synthesis of the fullerene. Fullerene is synthesized by the vaporizing the graphite rod in the helium atmosphere. That means in the present inert atmosphere, if we are going to vaporize the graphite rod, it is going to release fullerene. Evaporation of carbon using resistive heat. When an electric spark is struck between graphite rod, in all the above method, soot is going to be produced, which is mainly carbon black, and it contains significant amounts of carbon 60 carbon cluster compound, which are known as Buckminster fullerenes. Coming to the properties of fullerenes. Now this fullerene, it forms deep magenta solution when dissolved in benzene. It is very tough and thermally stable. Now this molecule shows, a single molecule can show its existence. So it is very tough and stable. That is, it exists as a discrete molecule. As I have said, a single molecule shows its existence. Now this fullerene, it can be compressed to lose 30% of its volume without destroying the carbon cage structure. Now the fullerene structure, it can be compressed to 70% of the original size, but this carbon cage structure is not going to get destroyed. That means it has very high stability. Now, a magnetic fullerene has been formed by mixing with an organic compound. Fluorinated fullerenes, they are also known as Teflon bulls. If we add fullerene to the fluorine to the fullerene C60, F60, then they are known as Teflon bulls. That means the strength of the fullerene increases many times. Now, talking about C60, this molecule has 60 vertices having 32 faces. By saying faces, I mean to say that the shapes of pentagons and hexagons, such type 32 faces are going to be present, out of which hexagons are the 20 faces, pentagons forms the 12 faces. Now this C60, it is a mustard color solid which looks brown and then to black on increasing the thickness of the material. The bond length of carbon double bond carbon is of the order of 1.38 angstrom, whereas the carbon single bond carbon bond length is of the order of 1.45 angstrom. Now, physically buckyballs, they are extremely strong molecules and they are able to resist very high pressures. They will bounce back to the original shape after being subjected to over 3000 atmosphere. That means even at high pressures, whatever pressure you are applying, on releasing the pressure, they are going to come back to their original shape. Coming to the applications of fullerenes. Now, on mixing fullerene with alkali metals, they form superconductors. One of the example is K3C60. Then these fullerenes, they take part in catalytic processes. They're also used as diagnostic agent due to size, stability and hydrophobic nature. Since fullerene is made up of carbon, it is a carbon compound C60. So obviously it is hydrophobic in nature. It is a non-polar compound. Then it acts as a potential inhibitor to HIV virus. Research is going on in this area and it is used for trapping small size ions from solution of water. Since fullerene, it has a buckyball shape, it has smooth, there are no edges present, sharp edges present. Therefore, fullerene, it can be used as lubricant because of the spherical structure. The ball would act as a molecular ball bearings. Fullerene, it can be made into a soft ferromagnet by reaction with tetrakris dimethylaminoethylene, which is TDAE, for the formation of TDAEC60. Then fullerene, it can also be used in the electronic, microelectronics and optical devices. Thank you.